Hello, and welcome to the Sentinel Innovation and Methods Seminar Series. My name is Rishi Desai. I'm an assistant professor of medicine here at the Division of Pharmacoepidemiology at Brigham and Women's Hospital and Harvard Medical School, and I'll be moderating today's session. The US FDA Sentinel System helps to address questions related to safety and effectiveness of marketed medical products. The Sentinel Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities. Sentinel Operations Center focuses on supporting the FDA in the use of Sentinel's common data model and associated modular programs or tools. We launched this webinar series to engage experts and innovators in key areas related to Innovation Center's master plan and Operations Center's methods work. With that, I'm really pleased to announce today's speaker, Dr. Jenna Wong. Jenna Wong is an instructor in the Department of Population Medicine at Harvard Medical School and Harold Pilgrim Healthcare Institute, where she also completed a postdoctoral research fellowship with Professor Darren Toh. She received her MSc in epidemiology from University of Ottawa and PhD in epidemiology from McGill University in Canada. Prior to her PhD, she worked at the Institute of Clinical Evaluative Sciences, or ICES, in Ontario, and her research focuses on generating evidence to inform appropriate and safe use of marketed medical products, particularly when they are used beyond their labeled indications without supporting data in real-world settings. She has extensive experience working with large EHR databases, including claims and EHRs. For today's talk, the title is Machine Learning in Distributed Data Network, like the FDA Sentinel System, Opportunities, Challenges, and Considerations. This topic, of course, is of great interest to us because we have been thinking about various machine learning approaches and how they can help the Sentinel system. And so before we get started, I would like to mention that your lines are muted. If you want to pose a question, please type it into the Zoom question answer feature. We will answer the question at the end of the session. Finally, this session is being recorded and will be made available publicly through Sentinel's website, which can be found at sentinelinitiative.org. So without further ado, I would like to hand over to Dr. Wong, who will be walking us through her recent paper. So thank you very much again for joining us, and take it away.
Great. Thanks for that introduction, Rishi, and thank you for the opportunity to give this presentation on the last seminar of 2022. So today's presentation is based on a review paper that I published earlier this year with Darren and Rishi from Sentinel, as well as other collaborators from the Odyssey and Eden Distributed Data Networks. So like the paper, the spirit of this talk is not meant to delve into the technical details of machine learning, but it's really meant to present a high-level thought-provoking discussion, discussing different connections between a broad range of concepts that many of you may be familiar with, and discuss how they relate to the use of machine learning in distributed data networks. So for useful references on any of the topics that are discussed today, or if you'd like to read more on the discussions that are raised today, then I would invite you to refer to the paper. So today's talk, I'm going to open with a few words about machine learning in healthcare and distributed data networks. Then I will talk about the key activities of distributed data networks, like the Sentinel system, that conduct activities in medical product surveillance and comparative effectiveness research, and talk about how machine learning can be used to enhance their key activities. Then in the next section, we'll switch gears a bit and talk about practical data-related factors that affect how distributed data networks work in practice. Then in section 4, we'll combine the discussions from the two previous sections and jointly consider how the opportunities for machine learning are affected by the practical data-related characteristics of distributed data networks. And we'll consider different challenges that arise through looking at 4 different scenarios. And then finally, I'll close with some additional considerations. And the pictures on the right are just a reminder that today's talk is really a high-level talk that's meant to see the forest for the trees without getting into too many details. And also that the discussions earlier on in this talk may seem like they start in disparate places, but the concepts will join up together, and we'll consider them jointly in our 4th section, where we talk about different scenarios of distributed data networks. So with that, we'll start with looking at a sample of papers that have been published this year in prominent medical journals that, based on their titles, you can see have used machine learning for many different types of applications in medical research, as well as applying them to many different types of electronic healthcare data. So it's clear that over the last decade or so, machine learning has really had an impact on the landscape of healthcare and medical research. But the term machine learning is often used quite loosely. So I wanted to start by taking a moment to define what I mean by machine learning in the context of our discussion. So this paper by Beam and Kohane present machine learning as a spectrum, and algorithms can exist along a continuum where on one end, the algorithms could be fully human guided, and on the other end of the spectrum, algorithms can be fully machine guided. And the degree to which an algorithm can be considered an instance of machine learning depends how much of its structure and parameters are predetermined by humans. So for algorithms that are determined by human decision-making, they would sit low on the machine learning spectrum. And then above this would sit regression analyses that are commonly used in epidemiology. And so for these types of models, while the model parameters are often determined by machines, the structure of them are heavily still dependent on human decision-making. So above these algorithms on the machine learning spectrum would sit more flexible, non-parametric algorithms like random forests or deep learning models like convolutional neural networks and generative adversarial networks. So these machines sit higher up because they rely more heavily on the machine to determine the specifications and parameters of the algorithm. And so in this presentation, when I'm referring to machine learning, I'm really talking about algorithms that sit higher up on this machine learning algorithm. And another observation from this figure you can see is that in general, the higher up the algorithm on the machine learning spectrum, in general, the larger amount of data is required to fit these algorithms. So multi-database studies provide access to more data through assembling larger and more diverse study populations. And there are many well-recognized benefits of multi-database studies, which include more generalizable findings, greater capture of rare exposures and outcomes, and better ability to investigate heterogeneous treatment effects. But we can add one more advantage to this list, which would be it provides more data for machine learning algorithms. One approach for conducting multi-database studies is through the formation of distributed data networks. And so the key traits of distributed data networks are that the data partners maintain full control over the physical storage and use of their data, and their source databases are not pooled centrally. So the source data sets can choose to share their de-identified individual level study data sets with the analysis center, or they could choose only to share aggregate level data, or even some sites could choose not to participate in a study if they so choose. So the main underlying point is that the control always rests at the level of the data partner in all uses of their data. So here's an example or a table showing well-known distributed data networks around the world that conduct studies in medical product safety surveillance and comparative effectiveness research. So for today's talk, much of the discussion will focus on the Sentinel system, but in general, all of the concepts and opportunities and challenges that we discuss really apply to all of these types of distributed data networks. And just to orient everyone, I thought I would provide a brief snapshot of the FDA Sentinel system at the current time. So currently there are 13 different data contributing sites, and it accrues currently new data on around 64 million individuals across different regions of the US. In total, there's over 870 million total person years of data that offer billions, tens of billions of medical encounters and pharmacy dispensing observations. And the Sentinel system contains access to a broad range of different types of electronic health data, from administrative data to more recent additions of clinical data on vital signs and patient-reported measures. So clearly, the Sentinel system contains a very large amount of electronic health data and rich electronic health data as well. So it's led to a great interest to see how these more powerful machine learning methods could help or could be leveraged to help utilize these data to the fullest extent in the activities of the Sentinel network. So with that, this figure here shows the key activities of distributed data networks that perform activities in medical product surveillance and comparative effectiveness research. So starting from the left, the first activity is computable phenotyping. So this refers to the process of deriving computable phenotyping or computer executable algorithms to identify patients with certain diseases, health conditions, or clinical events that can be measured from measurable patient characteristics. And so these computable phenotyping algorithms are used to create study measurements that are then used in downstream activities of the network. So these downstream activities include safety signal detection activities that generate hypotheses about new or unsuspected adverse events that then will be followed up for investigation of potential causal associations, which leads into the third activity of distributed data networks, which is causal inference. And these test hypotheses about the effects of medical products, especially compared to other medical products. And then the fourth activity of distributed data networks is forecasting. And so these activities predict the risk of future health events, and they help inform planning and prevention efforts. So now the question is, how can machine learning enhance the use or enhance these activities? So for this discussion, we'll just consider a single database setting and see what benefits we could expect to gain by applying these more data adaptive methods. So for the first activity of computable phenotyping, machine learning could be used to help determine the mapping from the inputs. So these could include biological, behavioral, or clinical features to the phenotyping status, but using a machine-guided process. And this is especially valuable for conditions where it may consider a wide range of clinical features and rely heavily on clinical judgment to make the diagnosis. So in this case, sometimes the mapping from the inputs to the phenotyping status is not explicitly apparent. So machine learning in this case can help use a data-driven process to find that mapping. Another use of machine learning is to extract potentially relevant phenotypic information from unstructured data via an automated process. So if this is applied to unstructured text, that could be part of a machine learning-driven natural language processing task. And if applied to images, it could be part of an image recognition task. For the second activity of safety signal detection, machine learning could be used in various ways, such as to directly estimate certain disproportionality measures. So for example, the information component is one Bayesian disproportionality measure, which is estimated using Bayesian confidence proportion propagation neural networks. Another use for machine learning is to reduce potential confounding by helping estimate general propensity scores. to help reduce the number of false signals that may be generated. Machine learning could be used in other innovative approaches with longitudinal observational data. And this is a really active and evolving area of research where there are many different types of studies, but I'm just here giving one such example. So here I'm showing one study which the authors trained a random forest classifier to predict adverse drug events based on vectors of features that consisted of association measures created from various cohort designs that addressed Bradford Hill causality criteria. So this is just one example of an innovative way machine learning could be used, and there are many others. And finally, machine learning can also be used for, again, information extraction, but this time to extract information on adverse events and also mentions of drug adverse event pairs from unstructured data using an automated process. For the third activity of causal inference activities, in this case, machine learning could be useful to automate various aspects of the high dimensional confounding adjustment process. So one aspect of this could be to use machine learning to help estimate properly specified nuisance functions. And so these nuisance functions in causal inference are not of direct interest, but they are necessary and used as a means of obtaining more consistent estimates of the causal parameters. And the extent to which they are properly specified determines how consistent the estimators are. So it's of interest to use machine learning to help estimate these functions. So I've listed here various ways that machine learning could help estimate properly specified functions. So this could include reducing dimensionality of the candidate covariates, prioritizing which ones to include in the nuisance function, helping estimate the correct functional form. And when used with ensemble learning methods like superlearning, it could be used to simultaneously consider multiple candidate covariate sets for the nuisance functions. And I should mention examples of nuisance functions would be like propensity score models or outcome prediction models that are conditional on candidate covariates. Second use for machine learning in causal inference, again, is like the other, in the other tasks, is also for information extraction. And in this case, it'd be to extract information on candidate covariates for the nuisance functions from unstructured data. And finally, for our last task of forecasting, forecasting can also be, or another word for it is prognostic modeling. And prognostic modeling shares many similarities to the task of diagnostic modeling, which we discussed earlier. So diagnostic modeling can be thought of as another way of talking about phenotyping activities to identify patients with certain medical conditions. So previously, we talked about how machine learning could be used to help determine the mapping from the inputs to the phenotype status. So for prognostic modeling activities, machine learning could again be used to determine the mapping from inputs, but this time to predict the risk of future health events using a machine-guided process. And for information extraction, instead of extracting potentially relevant phenotypic information in prognostic modeling tasks, machine learning could be used to extract potentially relevant prognostic information from unstructured data. Okay, so we'll switch gears now and we'll talk about several practical data-related factors that affect how distributed data networks work in practice. So here I've listed 3 data-related factors. The first being the modality of the source data that the data partners in the distributed data network use for the study. The second factor is the degree of standardization of data across data partners in the network. And the last data-related factor is the granularity of the data that the data partners choose to share with the analysis center. So we propose that for each of these data-related factors, there is a spectrum of possibilities that a distributed data network could fall along for these for each of these factors. So, for example, for the modality of the source data, on one end of the spectrum, we could have a network where all of the data partners use only data, structured data from their source systems in the activities of the network. And on the other end of the spectrum, we could have a network where all the data partners use unstructured data from their source systems. And currently, most distributed data networks are using mostly structured data from their source systems. But there is increasing interest to incorporate more unstructured data into their activities. So the trend is really to move rightward on this spectrum. For the second factor of the degree of data standardization, on one extreme, we could have all data partners that standardize their source data into a common format. This is called a common data model. And on the other end of the spectrum, we could have data partners that leave their source data in the native form and instead adopt a common protocol. And so currently, many distributed data networks sit more on the left end of the spectrum where their source data has been standardized. And also, there has been a trend that distributed data networks that once used a common protocol have over time been observed to move towards utilizing a common data model. And I think this really goes to show the great advantages of creating a common data model and adopting a standardized format that pays increasing dividends for the network as it conducts more and more studies over time. And the last data-related factor in terms of the granularity of shared data, on one end of the spectrum, we can have a distributed data network where all of its data partners choose to share individual level data with the analysis center. And on the other end of the spectrum, we could have a network where all data partners choose only to share summary level data. And across distributed data networks right now, they are really distributed on both ends of the spectrum. And that's because this choice really comes down to the choice of the data partners, and they also may be limited by external factors like legal and logistic or administrative considerations. Okay, so now that we've laid the groundwork and we've talked about the different uses for machine learning, and we've also acknowledged some of the practical considerations of distributed data networks, now we're going to join these discussions together, and we're going to consider 4 scenarios of distributed data networks that are defined by different type of data-related characteristics. And under each scenario, we'll consider unique challenges for machine learning. And also present possible approaches for addressing these challenges, as well as highlighting how some Sentinel projects and initiatives have relate to these different approaches. Okay, so for the first scenario, I call it the base case scenario. We have a distributed data network that has all data partners that are using only structured data from their source systems. For the machine learning model, all of the inputs for the machine learning model come from the common data model that has been standardized and created for all sites. And then in terms of the granularity of shared data, all data partners share individual level data with the analysis center. So this scenario is called the base case because it is arguably the most simplest and straightforward setting for applying machine learning. And so this is because the use of only structured data facilitates the easier creation of the common data model, because the common data model also contains structured tables. The use of inputs for the machine learning models that are all derived only from the CDM facilitates the curation of the analytical data set that will be used for machine learning. And then finally, sharing of individual level data essentially enables the modeling procedure to advance with the same flexibility as you would enjoy in a single database setting. This is because you could just combine all of the individual level data sets across all data partners. So although this scenario is representing something that is logistically feasible, it still has considerations. So here, the main question is, even though it's technically possible to apply machine learning, it's the question of, is it scientifically valid and should it be done? To answer these questions, data partners would want to consider factors like what is the purpose of the machine learning model, and also what is the extent of suspected or known heterogeneity between data partners, and does it make sense to combine the data into a global model? So for example, if using machine learning to estimate a propensity score nuisance function, often it is thought that the exposure mechanism may differ across different scenarios. So in that case, it may be preferable to fit local propensity score models rather than a global propensity score model. Okay, so we'll move to the second scenario. So for the second scenario, all factors are the same as the base case, except for the degree of standardization of the data. So in this case, we have some inputs for the machine learning model that are not found in the common data model. So in this second scenario, the main challenges that arise for the feature engineering process. And in other words, this is because the information of interest that is the information of interest for the machine learning models falls outside of the CDM in the native and unstandardized structured data in the data partner source systems. And this scenario may be very relevant for distributed data networks using data adaptive machine learning models, because it's often of interest to consider as rich or as broad of a feature set as possible. So it may be highly likely that some of these features are not in the common data model. So there's a few approaches that data networks could use to address these challenges. So the first approach could be to standardize the unstandardized information and essentially expand the CDM or add additional accessory tables to complement the CDM. So this approach is incredibly resource intensive. And so a distributed data network would consider these decisions carefully before going ahead with them. But these decisions may be warranted if this extra information can either be easily obtained, and so adding it to the CDM is quite easy, or it's information that will frequently be used in future studies, so has a high yield for the effort that is put forth, or the information is urgently required. So some examples of how this happened in the latest Sentinel Common Data Model. For example, there was additions of a patient-reported measures table, which is clearly information that is very valuable for future studies and future information for machine learning models. And so that information, the upfront investment will be worth it in the long run. Another addition was the addition of SARS-CoV-2 lab tests to the CDM. And so that was obviously in response to an urgent public health need. And so that is one example of when a distributed data network might choose to add information to the CDM. The second approach is that the sites could just do a site-specific analysis. And so the sites could compare their results using the additional information, and then compare the results across sites and also with and without the additional information. So this approach may be preferred when the additional information of interest is only available in select sites, or the added value of using these unstandardized information is uncertain. And this second point might be encountered often with data adaptive machine learning models, because it's often unknown ahead of time which predictors will be most important in the model when considering such a large feature set. Okay, so we'll move on to the third scenario now. So in this third scenario, again, all of the other characteristics are the same as the base case, but instead, in this scenario, the modality of the source data is using both structured and unstructured data from the data partner's source systems. So in this scenario, again, it creates challenges for the feature engineering process in the machine learning pipeline. And this is because the information of interest, which is unstructured data, exists outside of the CDM in the data partner source system. So essentially, you could think of this as an extension of the challenges in scenario 2, where instead of this information being structured data outside of the CDM, it is unstructured data. And this is highly relevant for machine learning endeavors because, as we mentioned in the first earlier part of this talk, there are many opportunities to use machine learning machine learning to enhance the activities of distributed data networks that use information from unstructured data. So different approaches to address these challenges could be first, again, to do a site-specific analysis where all data processing and information extraction, which is done on the unstructured data, is done outside of the CDM and using a predefined protocol. A second approach that could be considered would be to incorporate the unstructured data into the CDM, and this could be done in a few ways. The first way is the simplest logistically to implement, and that would be simply to store the raw text as a single field within the CDM. But this creates very unwieldy storage requirements and also can create privacy concerns and problems when data partners regularly share their individual level data with the analysis center. The second approach would be to instead perform the information extraction up front and then encode the extracted information, the output of the encoded information into the CDM as structured data. So this approach is very resource intensive and may sometimes could result in loss of provenance of the data depending on the quality of the data extraction tools. But there are great benefits, which include that the information then is processed and ready in a machine analyzable form for future analyses. So the Sentinel system has done projects and work under both of these approaches. So for one example is a recently completed Sentinel project where the collaborators used machine learning based on features from both structured and unstructured data to create a phenotyping algorithm for anaphylaxis. And this model was developed in one Sentinel site and validated in another, according to an explicit and predefined protocol. Under the second approach, there is also an ongoing project which is seeking recommendations for how best to incorporate information that has been extracted from unstructured data and incorporate it into the CDM. So overall, you can see that this area is especially a very active area of research in Sentinel to push forward this goal of incorporating more unstructured data into the activities. And so for the last scenario we'll consider is the scenario where, again, all of the parameters are the same as the base case, except for the granularity of shared data. And in this case, the sites are only sharing summary level data with the analysis center. So in this scenario, it creates challenges for machine learning, and specifically now the machine learning fitting process. And this is because the possible analytic options that the network can consider is constrained by the inability of its data partners to share individual level data with the analysis center. So under this scenario, there are again, two approaches that that a network could consider. So the first approach is that all of the sites could fit site-specific machine learning models. So you could have each site fitting a custom model on its own data and comparing the results, or you could have one site fitting one model and applying the model in one or any other amount of sites within the network. So again, the Sentinel Methods project developing and validating an anaphylaxis algorithm is an example of how this approach was used. In a second approach, the data partners could collaboratively learn a global model. And so in this case, the sites would use their data to train local models and then iteratively update a global model by exchanging summary level parameters with the central site or whatever site is aggregating the local model. So obviously this approach is a lot more technically complex and logistically complex to coordinate between different partners in the distributed data network. But it has been successfully demonstrated for regression models, and it is an emerging and continually developing area of research for more complex types of machine learning models. Okay, so now I'll finally close with some additional considerations. So for the challenges that we talked about in the previous section, we considered that there were different approaches to address them. But I would argue that there is no real right approach for addressing any one of these challenges, that ultimately what it comes down to is that the choice of approach is a balancing act across three different factors. And so one is the performance of the machine learning model or the precision of the results that you get from the machine learning model. The second factor is the cost and effort that is involved. And then the third factor to consider is the level of privacy that can be maintained for all of the sites. So ideally, we'd want to maximize all three of these factors, but in practice, it is often impossible. So the best approach is often the one that achieves the best trade-off to fit the needs and the resources that are available to the distributed data network. And the relative weighting of these different factors could also be further influenced by factors such as the objectives of the machine learning task, the suspected degree of heterogeneity across the sites, and what the sample size is at each site. So that could further influence which approach would seem more feasible or more sensible for a distributed data network for a given task. And lastly, I want to present some additional opportunities for distributed data networks in using machine learning to address certain issues that often plague the use of machine learning in single database settings. So on one issue in terms of generalizability, in single database settings, often external validation of the models is rare and slow. But distributed data networks present the opportunity to conduct external validation quickly and easily. And this is because of the availability of standardized data across the different data partners, which facilitates the ability to run common programs and common code across the data sites. In terms of model transparency, in single database settings, often there might be a lower impetus to provide finer details about the modeling process or about the model itself. But in distributed data networks, there really is a drive for high transparency between the data partners because they're required to be able to replicate the process in order to create similar models from by adopting a similar process. And finally, in terms of model interpretability, in single database settings, there may often be less reason to try and interpret or explain the model outputs. Doesn't mean it doesn't happen, but there may be fewer factors that prompt the need for this. But in distributed data network settings, Often it may be of interest to have more explainable models or be able to explain and interpret the model outputs, especially when unusual and discrepant results are observed across data partners. And so this would prompt the need to identify what the underlying sources of data heterogeneity could be. And so in closing, from this presentation, I hope that you come away with the following points, which is that, first of all, there are many opportunities to use machine learning to enhance all of the activities that distributed data networks like the Sentinel System and other pharmacoepidemiology focused data networks do. Secondly, I hope you have gained an appreciation for the unique challenges that distributed data networks face. And these are over and above the regular challenges that are already encountered in single database settings. And this is because of the way distributed data networks are set up to function and complete their tasks. But in this presentation, we went over various approaches that distributed data networks could consider to address these challenges. And finally, there is a lot of ongoing work and efforts being invested by distributed data networks like the Sentinel System to address many of the challenges that I presented in this talk today. And so I think these efforts will likely pay great dividends in the years to come. And so I would suspect that the utility of machine learning in distributed data networks will continue to increase in the years to come. So with that, that is the end of my presentation. Again, I invite you to read this review paper if any of the points of our discussion piqued your interest. And there's a lot of great references in that paper. And with that, I'd be happy to take any questions or hear any thoughts from the audience on any of the points that we discussed.
Great, Jenna, thank you. This was an excellent overview of all the opportunities, but also challenges of machine learning when you are focusing on a distributed data setup. So thank you for doing this. I do see one question in the chat box, which I will ask you, but I also want to remind folks that you can type your questions in if you have any questions at this time. So the first question has to do with sample size. So for an anonymous attendee asks that for site-specific analysis, the sample size may be much smaller despite of the potential availability of more granular data. And so for rare events, this may be actually impacting the performance of ML model adversely. And so how do you kind of balance these two competing things, more granular data and less sample size?
Sorry, could you repeat the part about the more granular data?
Yeah, so one of the solutions that you described in one of your slides, when you have more information for specific data partners, one of the solutions was to conduct site-specific analysis
Right.
or build site-specific models. So this questioner asks about what do you do with the sample size in that case, because it's likely lower for some of the smaller partners.
Right. So I would say in that case, that would be a factor that you would weigh into deciding what approach is best for you. So when I think about tasks like, let's say, creating a phenotyping algorithm, in that case, maybe a better solution for the distributed data network would be to have a larger data network create their phenotyping algorithm and then apply that in the smaller sites. You almost leverage the higher sample size from another site to create a starting point from which a phenotyping algorithm could continue to be tested and then tweaked. So it brings back to the idea of model transportability.
Great. So we have one more question. Maria Kempner asks, first, thanks you for an excellent presentation. And then the question is, can you please speak to how you proceed when you fit a model at one partner and then cannot apply this model to another partner? Does this happen? And if so, what can be done and what are the steps?
Sorry, Sorry, again, was the question that you cannot apply it or you can
Yeah,
apply
so if you face a situation where you have developed a model at one specific site and then you want to transport it, but for some reason you cannot do that, how does this happen? If it happens at all, what can be done if it does?
Okay, I think there are a few different reasons why a model might not be able to be transportable. So one reason could be that the features that you are interested in are simply just not available in the other site. So in that case, I think, unfortunately, there's not much you can do, except maybe encourage the other site to collect that information. But for another type of transportability is maybe due to heterogeneity in the sites. And so that is a lot trickier to address because it's unclear what are the driving factors that why the model might not be transportable. And in that case, you might just consider creating custom models for each site because it's just not transferable, not better to use a model from another site rather than using a model or a data partner's own data to create another site. But then, of course, then you have to consider things like sample size and yeah.
That's great, thanks. Again, if anybody from the audience has any questions, feel free to type them in. But I'll ask a question, Jenna. So one of the things I think that has gotten some attention over the last few years was this issue of drift in performance over time. So once you build a model, a computable phenotyping model, for example, let's say, because things might change, different types of people represent with the same condition or treatment patterns have evolved. And this, you can imagine that this might happen in situations, especially when you are thinking about new drugs being marketed. So I was wondering if you had encountered any good references or applications for accounting for these types of drift in machine learning model performance over time. And what's your general feeling about this?
That's a great question. I would say, to me, trying to assess for transportability over temporal, would require, if you have a model and you're continually using it, you should probably intermittently try validate it on the model and collect whatever you're using it for. Let's say it's phenotyping, extract gold standard information on the cohort every so often, and almost just doing checks over time to make sure it works or is still having the same performance. And if not, then probably refitting the model on the newer data. Or I will give a shout out to one of the ongoing Sentinel innovation projects, which is looking at data harmonization across sites. So I know in this project, we've also talked about the interest in not only applying these data mapping techniques across sites, but also looking over time within a certain data partner to see if we can also pick up on temporal trends that are going on in the coding of the data over time.
Yeah, that's a great point. And thank you for bringing the example up. I think it's very helpful because in recent years, something that comes to mind is when you go from ICD-9 based coding to ICD-10 based coding, coding practices may have changed, which could impact the performance of a model like that. So that's very relevant and something that we should keep in mind. So I don't see any other questions, so I'll ask one more. One of the applications that you were describing, which of course is of great interest to us, is this whole improvement in confounding adjustment piece by being able to fit more or using more data to adaptively fit these propensity score models or disease risk score models or whatever type of confounding adjustment that you are trying to attempt. So in those types of use cases, do you think that there is a need to consider specific types of machine learning approaches, or are there approaches that exist that are useful for these types of applications? Because that's almost an ultra high dimensional setting of confounding adjustment. When you're talking about free text data, for example, you can really endlessly mine information, but at what point does that information stop helping? I guess is what I'm getting at.
Right. I would say my first thought is that I would probably prefer algorithms that work well in sparse data. So I think of things like random forests, and those are my go-tos that I always try first, because it often uses a greedy algorithm. So greedy meaning that it'll take the most predictive first and then work its way down. So often if a certain predictor doesn't have a lot of data points in it, it will just fall out and not be selected. So that's one nice feature of that, compared to if, let's say, you were fitting a deep learning model and you needed more data to get the parameters for each of the nodes, something like that. So yeah, I think I would select that. And also I would consider how much tuning needs to be done for the algorithm. So I imagine for causal inference activities, you often want a model where you would like it to have pretty good performance, maybe not the best, but it doesn't require so much tweaking. Whereas something for a phenotyping algorithm, you might be more willing to play around with all the parameters and do cross-validation to tune the parameters, because you really want like absolutely best accurate model you can have at the end. And so I think for causal inference activities, you might want to go with one that is more on average performing well, and you can apply to many different scenarios without having to worry about tuning it so much.
Great, that makes a lot of sense. Thank you, Jenna, for responding to that. Are there any more questions from the audience? I don't see anything in the chat box. Okay, hearing nothing, we can probably wrap it up a few minutes early. Thank you again, Jenna. This was an excellent introduction to various machine learning approaches in distributed data settings, and look forward to following your work in this space for years to come. So thanks again. And just as a reminder, this presentation is recorded and will be made available through Sentinel webpage. This concludes today's session. We will hope to see you again next time. We have an exciting lineup of speakers for the next year as well. So consider signing up for our future sessions. And thanks for joining today. Thank you.